Okay, good morning, Astronomy 1010. Welcome to our 7th lecture, our 6th lab. Today, you've graduated from Baby Physics Academy, more or less, and we're going to actually start learning about our first astronomical object, the sun. The sun is an important part of our solar system, and it's a complex ball of plasma that we would like to study so that we can understand later on how the planets change based on radiation from the sun and from its solar wind. And also, planets are a nice contrast. I'm sorry, the sun is a nice contrast to planets, which we'll be studying. Hey, Enrique, what's the name of that little guy again? I forgot the name of that dude.
That's Ted.
Ted?
Yeah.
Ted's pretty great. Okay, we got Ted in the house. We are ready to do this Monday morning, right? Okay. I'd like to remind the class, because I've been getting a few emails, that homework is due like on Saturday or latest Sunday morning. When I grade the homework on Sunday night, that's usually the end of it there. So please keep that in mind, because a few people keep sending me submissions at like Sunday at 11:59, and that doesn't work for me, okay? I'd also like to say that there were a few scraps from our radiation and light chapter that I did not cover, but I'm going to kind of just bring them into play as we go, I suppose. Okay. All right. So let's start by thinking a little bit about the sun. I'm going to do a share screen with you guys. And what we'll do is we'll take a look at a website for something called the Solar Dynamics Observatory. All I had to do was type in SDO, and sure enough, the first thing that comes up is the NASA webpage for the Solar Dynamics Observatory. So the idea behind the Solar Dynamics Observatory is that it's a spacecraft which orbits Earth, which is continuously pointing towards the sun and imaging the sun at a variety of different wavelengths. It has all these different cameras, a camera that can look at visible light, UV light, X-rays, infrared, you name it. And it's constantly orbiting the sun. Let's see if I can do this here. Let's go to the images so you can just see a little picture of it. So imagine this thing is orbiting around Earth, and it's constantly pointing towards the sun because it's in a polar orbit. And we capture images and video of the sun in real time. So if I can get rid of this thing, which is in my way, one of the cool things you'll notice on the front page there is this shows you an image of the sun at 19 nanometers. And this was taken probably today at 1500 hours universal time. You guys will remember that we're about 5 hours off from England, right? So this was taken, wow, 11:28, or about 5 minutes ago. And you can see that the images of the sun are constantly coming back at a variety of different wavelengths, and we can kind of see what the sun is up to on a typical day. So I took a couple of key videos, and I'd like to show them to you. Here's the first one. This is a video of the sun taken at 4,500 angstroms, which is 450 nanometers. And that is in the visible spectrum. Do you guys remember what color 4,500 nanometers is? Do we need a hint? 450 nanometers? What color is that?
Blue.
Come on, we can get more creative than that.
450.
We call this blue. What color is this?
Indigo, violet.
That's right, it's indigo.
All right.
So this is an indigo image, or they're taking a picture of the sun at or a video of the sun rather, at indigo wavelengths, but you'll notice they've kind of false colored the sun yellow so that you can sort of understand that this is what the sun would look like to your naked eye, okay? Now I want you to watch this movie and I want you to see what's happening here. I'm just gonna hit play. And you'll notice that the sun is rotating, and you can see that it's rotating because you can see, what are these things called over here? Really?
Black bodies?
No, you might consider the sun a black body, but these things are something that Galileo observed.
Craters.
Craters.
Sorry, not craters. The sun doesn't have a physical surface.
Oh,
Sunspots, says Brendan Moroli. He might be a troll, but he knows his sunspots. Okay, cool. You guys might remember that these sunspots are something that Galileo observed with his telescope. He eventually went blind because of it. We can use sunspots to track the sun. We might actually be doing that for lab, except we're a lab behind, so we need to do spectroscopy today. The point of this video is to show you that at visible wavelengths, the sun is kind of freaking boring, okay? It just sort of rotates, and the illumination that we get from the sun at visible wavelengths is very, very uniform. If we were to change our wavelength of observation, however, we would see that the sun is actually doing something totally different and looks much more insane. So whereas at visible wavelengths, the sun has a nice even illumination, I am going to show you another video, which is of the exact same time window on the exact same day. So it's the exact same day, except we're going to look at the sun at X-ray wavelengths instead. And you'll notice that the sun looks totally wild. And when I hit play, you can see some dynamic activity happening on the sun. You can see giant magnetic fields poking their way out of the surface of the star, and huge eruptions called solar flares at work. You're going to see a very massive solar flare over here in just a second or two. So we can see these magnetic fields building up energy and creating a burst. Oh, there you go. Look at that. That's a huge jet of plasma coming off the sun. We can also see things that we call prominences, which are vertical sheets of plasma sticking off the sun. Sometimes they call them coronal loops and coronal holes. It may be hard for you guys to appreciate just how big a sunspot is, or just how big the sun is in general. So why don't we take some notes on that so you guys can learn a teensy bit. Oh, we lost Ava. Okay, here we go. Some notes on the sun. At some point, I want us to sort of try to calculate the size of the sun and how big a sunspot is. Usually when we study the sun, there's two things that we start off by learning about. We learn about the sun's fixed dimensions. And we also learn about the sun's composition.
No. Eat. Okay. Oh boy.
I can hear some youngsters out there. There are 4 parameters of the sun that do not change, and we can use them to study and analyze the sun. They include the sun's mass, luminosity, temperature, and radius. The mass of the sun, by the way, oh, hey, someone might want to, let me see what's going on here. Show non-video participants. Somebody have forgot to mute themselves, Jacqueline, but that's okay because I just muted you for you. Okay, let's go back to it here. The mass of the sun is 2 times 10 to the 30 kilograms. That number does not change, nor does the luminosity of the sun. It's fixed at 4 times 10 to the 26 watts. The radius of the sun is 700,000 kilometers. And the temperature at the surface of the sun, the sun has a variety of different temperatures associated with it, but the temperature at the surface of the sun is 5,800 Kelvin, okay? These numbers are fixed and they don't change. And although this is the only star that you will be studying, when it turns out that in my class on stellar astronomy, if you know these 4 properties of a star, you basically know most of the physics associated with them. So these are good numbers to kind of just start off with so that you can learn some basic facts. Also, it's nice to know the composition of the sun. The composition of the sun is 70% hydrogen by mass, 28% helium by mass, and the remaining 2% of the sun is a mixture of all different kinds of elements from the periodic table. Astronomers sometimes refer to them as metals, but they're not only metals, they're basically just heavy elements from the periodic table. And those heavy metals could be kind of anything. They could be carbon, nitrogen, oxygen, silicon, iron, whatever, you name it. The list goes on and on. I'd like to point out that when a chemist says metal, that means something different than when an astronomer says metal. A chemist says metal when you're talking about nickel or iron or vanadium or gold. An astronomer, when they say metal, they just mean something that is not hydrogen or helium. Kind of a little shift in nuance there. Take a moment to get those notes down because they're kind of important. Let's see here. I'm going to do some troll hiding. Where do I do that? Okay, let's see how we can use these numbers to understand some cool things about the sun. I'm going to go ahead and share screen, and we're going to look at this visible light image of the sun, and we're just going to think about one of those little sunspots there, okay? I'm going to take out a ruler. I'm going to measure the size of the sun, and then I'm going to measure the size of one of those sunspots, okay? So I want you guys to write a couple of numbers down for me because I need your help. The diameter of the sun is 12.6 centimeters on my screen. So please write that down. I just measured 12.6 centimeters. The size of that big sunspot, the big sunspot is 4 millimeters, okay? And I want to see if we can figure out how big a sunspot is together. I'm going to erase this. Now, remember the sun has a radius of 700,000 kilometers. Let's play a game called How Big is That Sunspot? Okay? And what we'll do is we'll draw an image of the sun, and we'll draw an image of the sunspot. The sun is, well, if the sun is 700,000 kilometers in radius, what does that make the diameter of the sun? Don't think too hard about this, guys. 700,000 times 2.
$140,000.
Not 140,000. That would be less.
Is 1.4 times 10 to the 6.
1.4 million, right? I just wanted to make sure some brains were working this morning. It's Monday after all. Life is hard. 1.4 million kilometers. It's kind of hard for you guys to understand just what a stupid big number that is. The sun's freaking huge. 1.4 million kilometers. And when I measured it on my screen, it was a mere circle. What did I get? 12.6 centimeters. And I measured 4 millimeters for the width of that sunspot. Can any of you guys think of a cool way to figure out how many kilometers that sunspot would be in real life? I wonder if anyone has any problem solving skills there. Noah, you just jumped onto the scene here to rescue us, right? Isn't that right, Noah? Noah, you showed up just in time to help us. I think he just logged in. Listen, Noah.
Yeah.
Noah, I got some work for you, buddy.
All right.
If the diameter of the sun is 1.4 million kilometers, but I measured it on my screen to be 12.6 centimeters, I should be able to use that to figure out how big a sunspot is. When I measured the sunspot, it was only 4 millimeters in diameter. Do you have any thoughts about that? I know you just got here and all, but
I would say put 12.6 centimeters like over like you basically find the ratio and then
ratio of these two.
or the scale, I guess you'd call it.
I got an idea. The thing you're suggesting is a very good way to do things, and you could come up with a corresponding ratio, right? Like this is to that as this is to kilometers. But we can also do it by dimensional analysis too. We could start with our 4 millimeters, right? And we could argue that we have a conversion factor. We have something called a scale model. And in our scale model, 1.4 million kilometers is equivalent to 12.6 centimeters. Noah, I want you to imagine that that's like a conversion factor, and let's do this dimensional analysis style. I want to know how many kilometers that 4 millimeters represents. Did I lose you, or are you with me?
Oh no, I just connected my AirPods. I missed that.
Is anybody else besides Noah with me? Noah just got here, so he's a little shell-shocked. How about the rest of you guys? No? No deep thoughts? Everyone's like, hey, watch this. I'm going to hide too, okay? All right, never mind. I can't do that. No
do you want
thoughts?
to turn it into centimeters first?
Okay. There's a difference between these kilometers and these centimeters.
Right.
These kilometers are real kilometers in space, but these centimeters are fake centimeters. Oh, do you mean the millimeters? You mean the millimeters?
Yeah.
Yes, that's a grand idea. Let's do that.
Millimeters on the bottom, centimeters on top.
You'll notice I'm using a prime because these are fake centimeters or fake millimeters. They were on my computer screen. And what's the conversion factor?
It's going to be 1 centimeter for every 10 millimeters.
Okay. So that basically gives us 0.4 scale model centimeters. Now what do I do?
Again, I would do it the way where it's like you find
the ratio. But
right.
that turns out to be the same way as the dimensional analysis way, Noah.
Oh, really?
Yeah, so since you already know the ratio way, I'm going to show you the dimensional analysis way.
Oh,
so let's just
could you multiply it by this 12.6 centimeters prime over?
Wait. Remember that the rule to not screw this up is units first, numbers second. Let's put our units in place.
All right, so the centimeters prime, and then kilometers on bottom. Oh, wait. No, that's backwards.
That don't make no sense, does it? All right. So centimeters prime on the bottom, otherwise centimeters prime don't cancel, right?
Right.
All right, and now tell me where my numbies go.
So 12.6 on the bottom.
That's right. And 1.4 million on the top, because that's your conversion factor. That's your ratio, Noah. Okay, punch them up. Take out your calculators and do something, you lazy bastards.
I got 4,400 kilometers.
I was expecting more, Bella.
Well, it says 0.444, so that's what I got. That's why.
No, I mean, you screwed up somewhere. You read the number wrong or you punched it wrong. It's not about precision, it's about magnitude. Your number should be bigger than 4,000. Bella, I suspect you had the right number. Cam, I want you to read it to me. I'm done looking at your calculator. You have to interpret the numbers for me.
I got 44,444.
Okay, whoa. Let's slow down with the fours there. Precision, 2 sig figs. Say it again, Cam, this time rounding to 2 sig figs.
Okay, 4.4.
No, I'm not asking for scientific notation. This number is not bigger than 1 million. I want you to round it to 2 sig figs.
Okay. So it would be 44,000?
That's what I want to hear.
Okay.
44,000, Bella, not 4,000.
Yeah, I realized that afterwards.
What are my units?
Kilometers.
Now, I need you guys to think critically about this. A sunspot is 44,000 kilometers, but Earth has a diameter of 6,400 kilometers times 2. That's the radius of Earth, is 12,800 kilometers. So what's my point, class? What's my point?
The sun is huge.
Well, that's kind of my point, true, but I want something more quantitative. How does the size of that sunspot compare to the size of Earth? Take the ratio. I'm feeling abusive today, guys. Take the fucking ratio.
The sunspot is almost 4 times as big as the Earth's diameter.
Yeah. Sunspot is, when I did it, I got, well, 4 is fine. I got 3.5 times bigger than Earth.
I said almost 4.
And you did good. Whoever I'm talking to there, that's I was plenty okay with 4. I decided to give one more digit of precision for fun. But I almost wrote down 4. I don't know why. I felt like doing 3.5. Just matter of personal taste. In other words, think about it. If come on. If this thing here, yellow is not going to work. If this guy is 4 times bigger than Earth, just think about the whole giant sphere you've got here. It's massive. It's insane. No wonder it actually rotates quite fast, friends. It appears to be rotating slow because every hour, this thing is moving by 4 Earth diameters or so. It looks like it's moving about 1 big sunspot per hour. So this thing's actually moving quite fast. It just doesn't look fast because you're looking at a ball that's 1.4 million kilometers in diameter. It also makes you realize that some of the stuff that we see on the sun it must be truly wild. Like, let's take a zoom in on one of those solar flares here. I'm sorry, let's try this. These coronal loops happen when magnetic fields, okay, let's skip the space music. And watch this. Here you can see a magnetic field pushing plasma up off the surface of the sun. And the plasma turns out to get stuck to the magnetic field lines. So as the magnetic fields are pushing up off the surface of the sun, you're basically going to see a plasma waterfall that's like 6 or 7 Earths tall. There's the Earth to scale, by the way. And these magnetic fields interact with plasma in complicated ways. They push plasma off the surface of the sun. Notice that the sun is kind of bubbling like a cauldron. There are all these little mini eruptions happening at the surface of the sun due to interactions between convection and magnetic fields. Sometimes the magnetic fields build up a lot of tension and they can create epic explosions. Sometimes we call them solar flares, but the really violent ones we call coronal mass ejections. And I want to show one to you. Watch this thing. Boof. Look at that. That's a massive eruption of plasma on the surface of the sun. The sun's actually kind of wild and it's violent. It's a very violent place. All right, let's try one more little math exercise because I think it's a good idea for us to do this. I told you that 2% of the sun's composition is in the form of heavy elements. Okay, I want to try this problem. What is the mass of the 2% metals in the sun? I was thinking that would probably be a pretty easy question, right? How would we want to do this one?
Will we have to compare it to Earth?
We'll do that at the end. That's a great idea. But first we have to figure out how many kilograms the 2% metals comprise.
Could you just do 2% of the mass of the sun, or is it going to be different?
No. It's just that stupid. It's just a test to make sure that we can handle something. Yeah, just do 2% the mass of the sun. So how do I set that up? The mass, well, how do I write 2% as a decimal?
0.02.
Times the mass of the sun, right? And when we wrote, what did we have for the mass of the sun from our previous notes?
Times 10 to the 30 kilograms.
We actually really don't need a calculator for this. What's 2 times 2? 4. Now this is 10 to the negative 2, right? So if this is 10 to the power of minus 2, 30 minus 2 gives you 28. 4 times 10 to the 28, and the units are kilograms. Now Frank suggested we compare that to the mass of Earth. Great idea. If we compare to Earth, we get 4 times 10 to the 28 kilograms over 6 times 10 to the 24 kilograms. Why don't you guys punch that up for me?
Do you want 2 sig figs?
Yes.
After rounded, I got 67,000.
Wait, 67,000?
Oh wait.
Say that again,
Well,
Jake. Say it better this time. Say it correctly. 67,000 means 67,000. That is not the number you got.
700.
Yeah, 6,700.
6,700, or Jake, 6,700. Okay. You get me now, right, Jake? 6,700?
yeah.
That's okay. We're learning to talk numbers. That's what we're doing here. 6,700 times greater than Earth. 2% of the sun's mass might not sound like a lot, but if you could extract that 2% heavy elements from the sun, you could make another 6,700 planets in our solar system. That's freaking nuts. I think that's the point, the message that I'm trying to make is to teach you something about the solar system, okay? The solar system it's the sun, okay? That's all the solar system really is. What? Come on. Where's the damn wiki page? Here we go. The solar system is the sun. That's what it is. The planets are part of that little 2% heavier elements that didn't quite make it into the sun. They had too much angular momentum or something. But the sun is a truly epic sphere. And the sphere is mostly made of hydrogen and helium with what I would like to say are small amounts of other stuff. But as you can see, the 2% other stuff actually could make another 7,000 planets. So that ain't small to you, kid, okay? That's epic. And let's just even consider that most of the sun is hydrogen and helium, and we should study that a bit, all right? I'm going to erase this. Are you prepared? Okay. I'm going to try to make a point about the sun. We're going to have to kind of talk about gases. The sun is not a solid surface like the Earth is. It's a gas ball that gets thicker and soupier as you go down into it. And in that sense, the gas will slowly get denser and hotter and more compressed. We're going to have to talk about gases and pressures and temperatures. So let's start off with this note, okay? We could say that the sun is a mixture of two things. We could say it's a mixture of neutral gas and plasma. And what I'm worried about is I'm worried that you guys have no idea what these two things mean, which is probably a pretty good assumption. So let's start by considering some hydrogen atoms. Do y'all remember what the composition of a hydrogen atom is? What is a hydrogen atom comprised of? Nothing? It's in your notes.
But a hydrogen atom?
Yeah.
All right,
Google
I
it.
got you.
Do something.
Oh, a hydrogen atom, protonium and deuterium.
Sorry, that's protium and deuterium. Most
Yeah.
hydrogen is in the form of protium. So what the hell is a protium atom, Andrew?
Protium. Is it lighter? Isn't one of them lighter? Because I know.
I'm not asking you to
deuterium is
weigh them.
heavy.
I'm asking you to tell me what they're composed of, like their particles.
Oh, neutrons, electrons.
Not protium.
Oh, electron and a proton.
Thank you. 1 proton, 1 electron. So let's draw some atoms here. Here's a proton surrounded by an electron, okay? Here's another proton surrounded by an electron. Here's another proton surrounded by an electron. This is what a neutral gas looks like. It's a bunch of atoms that have the electrons bound to the nucleus. That way they are neutral and there is no net charge. That's what neutral means, right? Neutral means 1 proton, 1 electron. Of course, the hydrogen is intermixed with helium. So if you really want to know, the gases inside the sun probably act a little bit more like this. Function F519. Here, the blue pellets might represent hydrogen atoms, and the red pellets might represent helium atoms. That's the rough ratio. They're all kind of bopping around and moving around together. Because the gas particles are neutral, that means they behave like ping pong balls in a box, or they behave like billiard balls on a pool table. They travel in straight lines until they stupidly crash into each other, and then they stupidly reflect off each other in some logical way, and then they bounce off in some other direction, all right? However, not all of the sun is neutral. All of the mischief shows up because some of the form of the gas is plasma. And plasma is not neutral gas. A plasma is a charged gas. As you raise the temperature of a gas, collisions become so violent that you end up knocking electrons right off of the atoms. And when that happens, you have a soup of charged particles. You have protons and you have negative electrons, which are all moving independent of each other. Well, not really independent, but they're all affecting each other. They have random velocities. They're moving in different directions. The moving charges create currents of electricity, and they create magnetic fields. So this kind of a thing doesn't just bop particles off of each other. These moving charges create magnetic fields. They create magnetic fields. And they also collide with each other in very complicated ways. Guys, while you write this down, I'm going to just turn the heat down in my apartment. It's a little warm. I'm going to erase this, but it looks like a couple people are still writing. So Adam, give me a thumbs up. Andrew, give me a thumbs up when you're ready to go. Okay. Matt, you cool? All right. Now, I want to explain to you what parts of the sun are plasma and what parts of the sun are neutral gas, but it's a little bit awkward to do that. So let me say that the sun starts off as it's pretty hot. So it's hot on the outside, right? The temperature at the surface of the sun is 5,800 Kelvin. And at the surface of the sun, it's maybe, I'm going to just do a rough measurement here, 1% plasma, and it's maybe 99%, we'll just call neutral gas for fun. As you get towards the center of the star, it gets insanely hot. The temperature at the core of the sun is estimated to be a whopping 15 million Kelvin. At that temperature, your sun is 100% plasma and 0% neutral gas. So out at the surface of the sun, there's more gas than plasma, and at the core of the sun, there's more plasma than gas. Because plasma is a type of gas, it is okay to say the sun is a ball of gas. Because most of the sun is in the form of plasma, it's also okay to say the sun is a ball of plasma. Sometimes I say both. Try not to get confused. There are differences, though. Okay. We would like to understand how gases work. And to understand how gases work, I need to teach you a little bit about this animation. This animation here is an animation of gas particles smashing into each other. And gas particles obey something called the ideal gas law. It's a math equation that relates three different properties of gases. I'm going to have to erase here. Now, when I studied chemistry in high school, they taught me the ideal gas law as PV equals nRT. That's a version of the ideal gas law, but it's a lame-ass version. Astronomers, physicists use a different version of the ideal gas law. It's P equals NKT, where I'm going to define all of these variables here. P is the pressure of the gas, and the pressure is measured in a unit called pascals. N is something called the number density. The number density of the gas is measured in particles per cubic meter. That's the number of atoms in a cubic meter box. Particles are kind of an abstract concept. So sometimes they suppress the term particles and they just write it as 1 over meters cubed. And sometimes when people are being real sons of bitches, they'll even just write it in this crazy old way. They'll write it as meters to the -3, because of course, if you flip the meter up, the power becomes negative. So if you see meters to the power of -3, you should know that that means particles per cubic meter, the number of atoms in a box. K is a constant of nature, and it's known as the Boltzmann constant. I'd just like to warn you that last class we learned about something called the Stefan-Boltzmann constant for black bodies. Not the same thing. Sorry, Boltzmann, you did too much cool shit and now we're all confused. There are two Boltzmann constants. There's the Stefan-Boltzmann constant and there is the Boltzmann constant. The Boltzmann constant it's related to gas dynamics, and it's 1.4 times 10 to the -23 joules per Kelvin. Kind of strange units there. Lastly, T stands for temperature. And that's, of course, measured in units of Kelvin. Okay, before we proceed, I need to know that you guys can remember things. What's the definition of temperature? We've learned this in our class up to now. If you can't remember the definition of temperature, I can't really tell you anything else. So I'll sit down here while you look it up because you probably already forgot.
It's the average kinetic energy of a system of particles.
Wow, Cam, you're good and you're fast. I like it. Temperature.
It contains either gas, liquid, or solid.
Right. In a way, do you remember what kinetic energy was?
It's energy associated with a moving object.
Right. So in other words, Cam, I wanted to remind you that temperature is the average kinetic energy of the particles, but what that sort of means in a touchy-feely sense, it means the speed of the particles.
Mm-hmm.
It's kind of like the speed of the particles. I'm just going to give you guys a second to catch up to me there. Oh, shucks. I forgot to get a hydrogen spectrum tube. Okay. I'm going to erase this. Okay. We're going to talk a little bit about pressure. So the pressure of a gas in pascals. Let's talk about pressure for a second. Pressure in physics is defined as force per unit area. And the idea behind pressure is something like this. If you have like a balloon and the balloon is full of gas, the pressure on the inside of the rubber membrane that makes up the balloon is the force of the gas particles sort of colliding with the walls of the balloon and bouncing off. As the gas particles smash into the wall, they deliver some kick or some force per unit area, per patch of rubber. And the force per unit area is the pressure on the inside of the balloon. For MKS units, force is measured in newtons. Area is measured in square meters. And newtons per meter squared are defined as a Pascal. Sometimes people just write pascals as PA. As an example, the air in your room air at sea level pressure, which is comparable to Rhode Island, usually has a pressure of about 100 kilopascals. And since kilo means 100, I'm sorry, well, since kilo means 1,000, sorry, that was a dumb. The pressure that you are experiencing right now is 100,000 pascals pressing against your skin. Humans are remarkably intolerant to changes in pressure. That's why your eardrums pop when you go up 30,000 feet in an airplane. It's an unpleasant experience. If you're a deep sea diver, it can be very unpleasant to experience underwater pressure. your body is accustomed and wants to be at 100,000 pascals of pressure. Can you guys think of any other units of pressure? What about you, like car enthusiasts, when you go out and pump your tires up at the gas station there? What units do you use for air pressure on your tires?
PSI
Yeah, what does PSI stand for?
pressure. I can't remember off the top of my head.
Well, it's
Pounds
a
per
force.
square inch.
That's right. PSI, thank you, Joel. Nice to see you. Is pounds per inches squared. It's a force per unit area. The air at sea level pressure is approximately 14.7 pounds per square inch. So that's the same thing as 100 kilopascals. Okay. There are going to be some other units of pressure that we use in this class, especially because I want us to have a whole lecture on atmospheres, planetary atmospheres. Sometimes we use a unit called 1 atmosphere, which is about 100 kilopascal. Meteorologists use a unit called bars, and bars are also about the same. 1 bar of pressure is also about 100 kilopascals. Why bars and atmospheres are slightly different is a long and unnecessary story, but usually if you watch the weather forecast, they use bars. If you talk to a planetary scientist, they use atmospheres. If you talk to a grease monkey mechanic, they'll use PSI. And if you talk to your professor in physics class, they use Pascal. Okay, that's how this game is played. Depending on your profession, you're going to use different sorts of units.
And is inches of mercury, is that?
That's also, yeah.
Like barometric pressure?
Yes, you can. There are other units besides these. So
okay.
Inches of mercury are, I believe, also, you can measure temperature this way too, but honestly, pressure and temperature are obviously related to each other, right? That's what the ideal gas law is trying to tell us. If you change the speed of the particles, you're going to change. If the mosh pit moves faster, then the force of the particles slamming into each other is going to be greater, right? In fact, to build up your ideal gas law intuition, maybe we could have a teensy bit of fun today. Every now and then it's nice to have fun. And what does fun mean? Fun means playing with our physics Java apps. Let's see if we have those here.
You have more pressure in tackle football than in flag football.
There you go. Now that's a plenty good analogy. More pressure in tackle football than flag football. I need your help with the sports analogies there. Okay, so gas properties. Let's see if my JavaScript is working today. It changes from time to time. Okay, cool. So let's just kind of build up our intuition. They're going to measure the pressure here in atmospheres. Let's pump it up. Pump, pump. Here come the gas particles. And let's see what they're up to. They're smashing around. They're about 300 Kelvin. Their pressure is just a little bit higher than atmospheric pressure. It's close to 1 atmosphere of pressure. By the way, room temperature at 68 Fahrenheit, that's 293 Kelvin. So this gas is both close to room temperature and room air pressure. What's going to happen if I add some fire and I apply some fire to the bottom of my box? That changes the temperature. How will the pressure react?
Exponential.
Well, it's actually not exponential, it's linear, because pressure is proportional to temperature. It is not proportional to temperature squared or cubed or fourth.
Oh, yeah.
So, but I'm not asking you about the curve. I'm asking you about just, is it going to go up or down or stay the same?
If you add heat to it, it'll go up.
The pressure will go up. So let's watch that. So here I am changing the temperature, and look at the pressure. It's steadily rising. Let's add some ice. Let's cool those atoms back down. You'll see them moving slower and slower and slower. And you see the pressure is dropping. Okay, let's just raise it up a little bit here. Let's see if we can get it up to room temperature and pressure. Ooh, just about there. Ooh, okay. What's going to happen if I take Mr. Robot and I squeeze the gas by constricting the volume of the box? What will happen to temperature and pressure, Matt?
Are they going to rise?
They are going to rise insanely. What parameter of the ideal gas law am I changing when I squeeze the box?
The room has to.
But that's not one of the
Fly through?
parameters. Choose from P equals NKT. I mean, in a
What's the question
sense,
again?
the question is, if I squeeze the box with Mr. Robot, what parameter of the ideal gas law am I changing?
Density and pressure? No, I mean pressure and temperature by consequence, but I don't know.
I'm asking which am I directly changing? Of course, all of them are going to change. Look, when I add fire or ice, I'm changing the variable T. When I squeeze the box, what variable am I changing?
Density?
Number density, but yes, if you have the same number of particles, but the box is smaller, the particles per unit box go up because you've got a smaller box, right? Does that make any sense? All right, anyways, just watch what happens. Watch this nuttiness. Ready? Squeeze. Look what happened to the temperature and the pressure. They went shitty bonkers. Oh my God, I blew the lid off this thing. Let's get that lid back on there. Okay. What do you think would happen if I added gravity to the situation? Let's try this again. Let's reset and let's pump it up. Pump, pump. What do you think would happen if I suddenly increased gravity from 0 gravity to lots of gravity? What does gravity do to gas?
It constricts it.
Kind of like the robot. So what should happen, Joel, if I add lots of gravity?
Should increase the pressure.
How about the temperature?
And the temperature. Because
all right, let's watch. Let's see if Joel's prediction is right.
If the pressure goes up, then the particles.
Look at that.
The particles will move faster because of the force applied to them.
Yeah.
Okay.
What you can see happening, Joel, is because the box is constant, the temperature went nuts. The pressure is kind of fluctuating a bit, probably because of the pressure sensor is up here instead of down there. The pressure would probably be greater if the pressure sensor was at the bottom of the box. Watch this. With lots of gravity, I can just open the lid. I'm going to add some light species too. Ready? With lots of gravity, I don't even need a box anymore, do I? Because the gravity is applying a pressure, keeping the gas squeezed down to the bottom. And a few particles bounce off here and there, but for the most part, especially the heavy particles can't escape because the gravity compresses the gas. It also heats it up. Holy smokes. I think we've just stumbled onto a concept. It's a concept in stellar astronomy. It's known as hydrostatic equilibrium, and it's kind of a big deal. Hydrostatic equilibrium is a balance between the gravity of a star and the thermal pressure that arises from the gas pressure pushing back out. They kind of come into balance and the star stays stable. In fact, this really answers the question, you know, if you think about it, the sun is a ball of gas that does not have a box, right? If you open up a bottle of perfume, the molecules scatter around the room. If you are in Star Trek and you open the hangar, the airlock doors, the gas rushes out of the spaceship into outer space. But why doesn't the sun do that? The sun's a ball of gas, but if you think about the sun keeps a perfectly fixed radius. And you know that the sun keeps a perfectly fixed radius because, cue up cheesy photograph here, you can see the radius of the sun on the sky with your own eyeballs. When you look at the sunset, you can see that the sun is a perfect sphere. And gases usually don't behave like that. They don't usually form into a perfect sphere unless there's so much bloody gravity that gravity constricts them into a sphere. Let's write this concept down because this is like a thing. And the thing is called hydrostatic equilibrium. It's a concept that applies not only to stars, but also to gas giants like the planet Jupiter. Introducing hydrostatic equilibrium. And I can define hydrostatic equilibrium this way. It is a balance of forces between gravity pulling in and what I will call thermal pressure pushing out. And by thermal pressure, I mean the ideal gas law. P equals NKT. At your knowledge of physics, all pressure is thermal pressure. But we have to say thermal pressure because in advanced physics, there are other types of pressures that are unrelated to temperature. Those are usually quantum mechanical in nature, but you don't need to know about that. That's over your pay grade. Hydrostatic equilibrium can be thought of in the following way. It answers the question, why does the sun maintain a fixed radius? So this answers the question, why does the sun maintain a fixed radius? That's a nice way to think about it. The answer is because hydrostatic equilibrium. Andrew, let me know when you're all set. Andrew, how you doing?
I'm almost done. I'm at the bottom.
All right. I'll sip some iced tea. Just iced tea sipping over here.
I'm all done.
Okay. I've got a few more concepts to explain. You know, in our first half of the lecture on the sun, we're covering some basic concepts that you have to kind of lock down. And then we'll get into some more nitty gritty next class. Let's talk about the sun's light production, okay? The sun emits two things. One is light, which is sometimes called radiation. The second thing it emits is particle emission, which is also called radiation. And unfortunately, these two words do not always mean exactly the same thing. From now on in our class, when I say radiation, I usually mean light. That's how a scientist, like a physicist, would think about it. But if you were a doctor, or if you were a nuclear weapons inspector, or you were like a Navy submarine operator, your version of radiation would probably be particle radiation, sort of like the type that Madame Curie studied, alpha, beta, gamma rays. In particle emission, Madame Curie discovered three types of particles that were emitted by radioactive objects: alpha, beta, and gamma rays. An alpha particle turned out to be a helium nucleus. A beta particle turned out to be an electron. And in a particularly upsetting mixture of the two, gamma radiation turned out to be a gamma ray, which is a form of light. So radiation can mean particle radiation. It can also mean light. When an astronomer says radiation, they usually mean electromagnetic radiation. Electromagnetic radiation is the electromagnetic spectrum, which you learned last week. Gamma, X-ray, ultraviolet, visible, infrared, radio. Remember that my acronym for electromagnetic radiation is YX-UVR. YX-UVR. Those are the bands of the electromagnetic spectrum. The parameter that quantifies how much light the sun puts out is the luminosity of the sun. And the luminosity of the sun is 4 times 10 to the 26 watts. You'll remember that last time I taught you that that is a heaping crap load of light. Okay, that's a lot of light. You could power the US for 4 million years with 1 second worth of that power, okay? On the particle emission side, we call it the solar wind. The solar wind is a stream of charged particles that's constantly being emitted from the sun. The solar wind has a profound effect on the planets in our solar system, which is why I'm talking to you about it now. But in fact, it's going to turn out the solar wind is actually related to the creation of the aurora borealis on Earth. But we'll get to that next class. I want to do some other things today. Today, I want to focus on just the light or the radiation that comes from the sun. But before I got into that, I wanted to give you a sense that the sun's giving off light and the sun's giving off particles. That's like a thing. Oh, maybe I could write down what particles the sun emits in the solar wind. It gives off protons, electrons. It also gives off helium nuclei, which you'll remember we call alpha particles. Lots of notes today, folks. I'm going to do one more little module for you before we stop and take tea break. I want to talk about radiation. Can I erase any objections here? All right. Last concept before we leave are the energy generation methods of the sun. So let's ask this question. How does the sun shine light? How does it give off so much energy, 4 times 10 to the 26 watts? Let's talk about incorrect ideas before I tell you how it does this. The first thing I'd like to dispel for you guys is that fire is not correct. The sun is not a ball of fire. And that's because fire is a chemical reaction. And it's going to be necessary for me to distinguish for you guys the difference between a chemical reaction and a nuclear reaction. So I'd like to do that now. Let's look at a typical chemical reaction, the kind that would create something called fire. So do I have a fire making apparatus here? Okay. So, here's one. I guess this is a butane lighter, but this is very similar to what you would see in the picture here. Here I have pellets of diatomic oxygen, which are in my room. So these are 2 oxygen atoms bound together. That's diatomic oxygen. The symbol is O2. Here I have a molecule of methane, which is 1 carbon shown in black and 4 hydrogens shown in blue. If you mix 2 parts diatomic oxygen to 1 part methane, you get a crazy violent chemical reaction where all of the hydrogens jump ship and leave the methane to attach to the oxygens. This releases so much energy that it heats up the air and causes the air to glow, which you call fire, okay? That's the energy being emitted in the form of light. And then the hydrogens end up stuck to the oxygen. That makes 2 parts water and 1 part CO2, carbon dioxide. Now, the sun does not produce light in this manner. If you did create a ball the size of the sun and you somehow filled it up with oxygen and methane, the sun would shine itself to death in 10,000 years. And that means that the sun can't be a ball of fire, otherwise the sun would have burned out long before before the dinosaurs even existed, right? We know that the Earth is billions of years old. So fire, believe it or not, is not efficient enough to account for the energy of the sun. Let's talk about another way the sun. Oh, yeah, ask a question. I'd like it.
Is lava the same thing as fire, or is it slightly different?
It's extremely different. Lava is something you're going to learn about because we're going to talk about planetary geology. And you will learn that lava is a form of high temperature rock. It's literally rock that has been sort of liquefied into a pool of liquid rock. It does glow and it does shine light, which is why you might be getting that mixed up into the mix there. But fire is usually in the form of gas, whereas lava is just rock that's been heated up to the point of liquefaction, and it does glow for a while, but it's not a form of fire.
So lava wouldn't be found in the sun?
Definitely not. Lava is in a solid or liquid phase, and it's made mostly of rock called basalt, and none of those minerals could even survive in the sun. They would be broken down into atoms. The sun is too high temperature for any solids or liquids to exist. It's just a ball of gas, C, plasma stuff, okay? Sometimes molecules can exist in the sun, but nothing as complex as a mineral, okay? Nothing solid at all. But reasonable question. Okay, next up is to tell you that stars can actually shine from their own gravitational contraction. And I was thinking that might not be such a crazy idea for you guys, because after all, where'd those physics Java apps go anyways? Remember that when I took this gas box, right? Come on, you stupid gas box. And remember that if I pumped the gas box full of gas particles, and then I went and I added gravity, watch what happens to the temperature. Bada boop. I'm sorry, but if you raise the temperature of gas to 1,500 Kelvin, that shit's gonna glow, okay? When things get that hot, they glow and give off light, and that light will shine away a bit of energy. So when the sun first formed, it probably did glow entirely due to its own collapse and contraction. That's when it's in a stage we call a protostar. But the issue, I'm trying to hide all this stuff so I can, where's my bloody slideshow here? Stars can shine due to gravitational contraction, but let's put some numbers on this. The sun could shine as a ball of fire for a total lifetime of maybe 10,000 years. That's going to be a homework problem. So the sun can't shine by being a ball of fire. Gravitational contraction that can cause a star to shine for a lifetime of, I believe, 100 million years. 100 million years probably sounds impressive to you, but even a basic course in geology will teach you that if you study the layers of rock in the Grand Canyon, you quickly discover that the Earth has to be way over 100 million years old. Like one layer of sediment might take 100 million years to form, a rock layer. So you can quickly count layers of rock and figure out that the Earth has to be billions of years old. It turns out there is a way the sun can shine for billions of years. And the answer to the question, how does the sun shine, is that it has a little energy generation, a little one. It has a whopping energy generation mechanism in its core. It's nuclear fusion. And nuclear fusion is a process in the core of the sun where hydrogen atoms gets fused into helium atoms plus a little bit of light. In fact, it takes 4 hydrogens to make 1 helium plus some light in the form of gamma rays. This reaction sequence, known as the proton-proton chain, is the nuclear fusion mechanism by which the sun generates light that then leaks its way out of the star. We're not going to get into that today because it's too detailed, but we'll try to cover it on Wednesday if there's time. For the moment, we've burned through another hour and a half of lecture, so we should pause there. The lab that we're going to do today is the spectroscopy lab, and that's going to take a few minutes for me to set up, and I could kind of use a little snack too. So let's go to Blackboard lab. And here's our spectroscopy. Spectroscopy is where we're going to analyze different types of light. This is the sheet that you need here. Now, a pack of colored pencils would be very helpful. If you have markers, colored pencils, or anything that you can make colors with, please get that and print this. If not, you may want to use a program like Microsoft Paint, and you might actually just want to paint the colored lines onto this spectrogram, okay? All right, so hey class, just because I'm going to have to say this every lecture now, when are our labs due? What's your latest time to turn in lab?
Sunday.
false.
Saturday
Maybe if you get
and
lucky, if you're
Sunday morning.
if you're crazy, Sunday morning, right, Andrew? But I'm tired of people telling me that they have until Sunday at 11:59 to turn in their labs and homeworks. You don't. You have until Saturday night at 11:59, or if you want to get really crazy, Sunday morning. But once I grade them on Sunday night, that's it. Okay, so I'm going to go print out my lab, and I will see you guys after a little tea break. Capiche? Thanks, Joel, for the reminder. Okay, welcome to our spectroscopy lab. Now that I've got my ducks in a row, I'll tell you once again for the nighttime students what your ducks need to be. You will need a copy of your spectroscopy paper here. Let me go to speaker view. It's 11-5, and it shows you some blank spectrograms with values in angstroms and some blanks for a gas name. I'm going to use my spectroscope to analyze some different types of light. When you look into the spectroscope on your camera there, let's see if I can provide a light source. Everything's kind of backwards. Shoot. The spectroscope allows you to take light and to break it into its component wavelengths, just like a prism, just like Isaac Newton did. So if I illuminate this switch here, you guys can see that my lighter produces a rainbow. Over here, you can see there are some numbers on this scale from 400 all the way up to 700. Once I turn the light on, it should be easier to see. I also have some colored pencils. The colored pencils are going to allow me to take the spectra of different types of elements. Now, if we could go back to our lecture from last week, explain the whole concept here. Remember that we can break light apart into its component wavelengths, and we can see different types of spectra. Most of the spectra you're going to be looking at today are kind of like emission line spectra. So you're going to see, for instance, when we study hydrogen, that you get a red, a blue, and a violet line. But there are other atoms in the periodic table that produce other types of spectra. These spectra are created when electrons jump from high to low orbit inside of an electron. And we just want to see if we can take the spectra of a bunch of different types of elements. We're also going to see some continuous spectra with no breaks. And I'm hoping to even show you an absorption line spectra. That's where an electron goes from low orbit to high orbit and leaves behind a black absorption line. So let's see if I can connect to my phone here. Also, I just need a minute because over the course of doing this a few times, I've kind of mixed up. So this is neon. We're going to want a neon.
Brendan, I copied it down. So I got everything. I got all the questions down for this lab.
When you say, oh, you mean like you wrote this down?
Yeah, I wrote that down.
That works just fine. If you guys don't have, all right, so here's my hydrogen. The hydrogen is the one I'm most worried about, class. Oh, I got some hydrogen today, so let's hope we don't screw this up. Okay, let's see if I can connect to my Wi-Fi and use my phone here today. Screen. This is going to require a little bit of skill on my part. I guess I can't go any lower than this. I'm going to have to see if I can use my phone and hold it to the spectroscope. First of all, let's share screen to my phone. It's going to make me reinstall the plugin, which it does every time. I don't know why. Okay. Seems to be working today. That's good. All right, so let me grab my pencil. And let's, of course, put our name up at the top. This is Lab 6. And of course, you are AS1010. Don't forget to put your section there, whatever it is. Okay. Let's write down the gas names that we'd like to look at. We'd like to observe hydrogen, helium, mercury, neon. I'd like us to look at incandescent bulb. I used to have us look at a fluorescent bulb, but I don't think I have. I'm kind of not into fluorescent lights for because they're ugly, but I don't think I have one here in my apartment. We'll also try to look at the solar spectrum. That'll probably keep us busy. So over here, I've got a setup, right? I've got a power supply that can heat up different types of gases. I also have an incandescent bulb. Maybe we should actually start with the incandescent bulb. The incandescent bulb produces a sort of continuous spectrum. And it might be nice for us to start there so we can see the complete rainbow. So let me go ahead and do that, right? Plug this in. This will also give me a warm up. So we're going to start here. We're going to start with number 5, the incandescent bulb. I just decided spontaneously that would be a fun one to start with. So let's hold up my phone, the spectroscope. I might even want to zoom in a bit there. And I've got to get the slot right over the line. And what you guys can see is you can sort of see a complete rainbow there. I'm going to go a little bit off axis. Just a sec. Guys, I have to photograph this. Hold on. This does take a bit of skill. All right, that looks good. The trouble with doing it through the camera is to make sure that we can get the wavelengths and the rainbow on the same axis there. That's a little bit fuzzy, so I'm going to try this once again. You know, if I could reduce the intensity, maybe if I stand a bit farther away, this would be a bit easier. Bear with me, guys. All right. Let's see if one of those is usable. So of course, you know what colors that I want to get out, right? I want to get out Roy G. Biv. And this is probably as good as I'm going to get. So I'll leave my phone there. And I'm going to grab out some colored pencils. I'm going to see if I can't get out a Roy G. Biv here. There's red, orange, green. So I got a blue, red and orange, a couple of different greens. Red. Oh, I still need an orange. Okay. I've got me a Roy G. Biv that's ready to go. Hold on, guys. All right. Keep an eye on that. Let's see if we can color. Notice the CCD camera doesn't do perfect justice to it. So what we're going to do is we're going to go down here to our incandescent bulb. I'm going to start with a violet pencil. And it looks like violet starts around 400. Okay, so this is my incandescent spectrum. It starts at, let me back up here. Starts at 400 with violet. And at some point it starts to switch over to indigo. Indigo is by the time we get to 450. So let's go somewhere around here. Let's see if I can see where indigo starts. It's a little difficult, but somewhere close to 450. This CCD camera doesn't distinguish the violet and the indigo that well. CCD cameras are usually pretty insensitive to violet light. So we'll start the indigo around 430 and go up to 450. Okay. There's our indigo. And then at some point, we're going to switch over to sort of cyan blue. And it's kind of hard to see the tick marks. I don't think this is a good one. Let's see if we can see here. See, it's weird. The purple came out like a streak in the middle. Let me move my student box here. So let me move you guys over to this side. So it kind of did this weird thing where there's like purple in the center and indigo on the outside. I don't know why that happened. Some kind of artifact of the CCD. But this is 400. Can you guys see my mouse? Can you see the little arrow mouse? Yes, Jay. Okay. So the little ticks are each 5 nanometers. The big ticks are 10 nanometers. So if this tick mark here is 400, 410, 420, 430, 440, 450 is usually indigo. 460, 465 or 470 is where the cyan blue starts, and it stops at 500. I'm kind of disappointed with these spectra. I've actually done this better before. Here it's a little too faint, but you can see the cyan is kind of in this range here. So we'll fake it until we make it. It's never going to be perfect. So let's get a sort of cyan blue. And we'll go for, notice that the spectrograms are backwards. A couple of things I probably should have told you before we started, but I was forgetting. Where's my pencil here? Sorry, guys, I had a pencil, but I lost it. On the spectroscope, the one that we've been looking at, they have the scale reversed, right? So they're using nanometers, and they have 700 nanometers, which is red on the left. And in the spectroscope, 400 nanometers is on the right, and that's violet. So they've got it set up to go Roy G. Biv, if you remember what that is. On these spectrograms, they're not using nanometers, they're using a unit called angstroms. And the idea is that 1 nanometer is equal to 10 angstroms. So if we get a line at 400 nanometers, that would be 4,000 angstroms, okay? So in other words, if we believe that the color of sort of light blue or cyan blue, if it's going from, say, 470 to 500, that's 4,700 to 5,000. So you'll see me color in. This is 4,800, so I'll start with 4,700. And I'll do sky blue all the way up to 5,000. That's how I'm basing my pictures here. Now, at some point, there's green, and then there's yellow. Let's see if we can distinguish the difference. It's kind of hard to see the numbers here, but that's 500 where green starts, and yellow seems to kick in. Let's see if we can find better numbers here. The green seems to stop and yellow seems to start. Yellow is actually a very narrow range. This is 500, 510, 520, 530, 540, 550, 560, 570, 575 is where yellow should sort of start. Okay, so green is going to be a big swath here. Start at 500, 520, 540, 560. So we'll go up to like 560. I could have shaded different shades of green, but I'm not getting that crazy. And now the yellow is going to kick in, and yellow is a pretty narrow band. I don't know if you guys can see this. Unfortunately, my pictures for the incandescent just came out really lousy today. Let's look at the one for our class. This is kind of cheating, but whatever. You'll notice when they get it right that yellow starts somewhere around maybe 560, and by 590 or 580 or 590, it sort of turns orange. So we'll try to reproduce that, right? So we'll have yellow start around 560. And I'll kind of stop it around 580. This is just cartoon style. And then around 580, I'm gonna kick in with some orange. Wait, are you guys seeing my thing here? All right. So 580, kick in some orange. And orange actually extends out to about 620 or so. You'll notice that somewhere after 600, boy, that looks like an 800. It's so lousy. I should just delete this. Let's give it one more try. This one, you can actually see the rainbow and the numbers. Oh, wow. I actually got it good there. Do you see that? That's better than we've had it. So you guys can see that orange extends out to maybe 610 or so, and then it starts to turn red. I don't know if this one came out any better. This one actually came out kind of cool. You can see more of the gradient, but it's not overlapping the numbers as well, unfortunately. So you can actually see it go here from violet to indigo to blue to green to yellow to kind of orange. Orange is also a narrow band. So we'll stop the orange here. I should have stopped it at 610, but I stopped it at 620. And then we'll just kick in the red. All right. And that's my incandescent spectrum. This is one of our more complicated spectra that we're going to look at today, but I decided to mix things up and to start with the incandescent because you kind of get a sense of where every color sits before we start looking at the bright emission lines. Does everyone have that? All right. Let's move on to try to do hydrogen now. Before I click on the hydrogen, I want to keep this way in the background here in hopes that it will help illuminate my spectrum a little bit. Let's see if that actually works. You can see it's going to illuminate from far away. And we want to just make sure those numbers are nicely illuminated. I'm not tuning on the hydrogen yet because it's going to burn out like 10 seconds afterwards. So you guys can see how I added a little bit of light to my spectrum there. All right, let's switch on the hydrogen. Notice that it glows a kind of cool electric purple color. Shoot, I'm losing the purple. Ah, rats. Could you guys see the purple line there for a second? I have to focus it really, really fast or it burns out.
It was like 4:30.
That's right. It's now too faint for the purple to be seen. All right, let's see if we can figure that out, Joel. Ooh, that was rough. That was a rough one. Okay, yeah, it's real fuzzy. But if we compare the tick marks to this is why I made a nice clean version of the spectrum, right? 400, 410, 420, 430, 440, 450. Let's see if we can analyze that again, Joel. Unfortunately, when the purple was there, I didn't quite get the numbers in focus. But you can see that's 400, 410, 420, 430. So we're going to go with Joel's estimate. So grab your purple, go to hydrogen, 400, 420, 440, and 430 should be right in the middle. Luckily, we got the other two in focus. What would you guys say the blue line is at?
Is that like 480?
480.
Yeah, I totally agree with that. So we'll go to 420, 440, 460, 480, make a cyan blue line. Okay. And that's, these have special names, by the way. This is known as hydrogen gamma. It's a very famous emission line. This is hydrogen beta. It's the 4-to-2 transition. And now we're going to do what's called hydrogen alpha, the red line. Okay. Give me the wavelength of the red line, guys.
650?
Yeah. And that's the spectrum of hydrogen. Hydrogen beta, hydrogen gamma, and this is known as hydrogen alpha. Let's check out our precision. and see how our numbers correspond to the true values by quickly looking at the chart from our slideshow. Kind of nice to just see how accurate are we? How close are we to the true values? In their more advanced ones, we got 650, they got 656.3. So we're good to about 2 significant figures. We got 480, they got 486. We got 430, they got 434. But do you want to know what I'm impressed by, guys? We got the first 2 significant figures just with our crappy little student spectroscope, right? So I think getting the first 2 sig figs good that's actually very hopeful, if you ask me. That means we're doing a good job. All right, let's move on to helium, which is luckily not as burnt out as my hydrogen. Now, I got to be careful here because this stuff gets piping hot, and I don't want to burn my fingers because then I'll have to sue myself. I can't sue anyone else anymore, so I'll just have to sue myself if I burn my fingers. Oh, geez. Okay, we're going to need, stand by there, guys. I need to get my plug, okay? But where to plug it in is the question. All right, good thing I bought that extension cord. Okay, now I should have juice. So that'll prevent a shutdown here. Sorry, guys. This is home laboratory setup. So, you know, this is how it goes now. So we were looking for helium before I was so rudely interrupted. Helium. Oh, I want to try an experiment, guys. I have a lens that I found. I found this in my drawer the other day. Someone left it here. It's kind of cool. It's like a little iPhone lens. Where am I here? And I wanted to try to put it over my camera and see if it improved the qualities of our labs. So let me take my phone out of my case for a second. I don't know if this is going to work, but it would be pretty freaking cool if it did. I used this thing once a long time ago. I don't really remember how to. Oh, push it over there. Okay, well. Oh, here we go. Oh, how does that look? Is that any better? Kind of like a higher quality lens, right? Can you guys tell if that's a better?
I think it has a wider angle.
Oh, a wider angle? Is that good or bad? I don't know.
You
I
can
just
see
see
more
more
to the
lines.
side. Mm-hmm.
Let's see what happens when we look through it with this. Do you see how it's over my iPhone now? I forgot. I just remembered like an ex-girlfriend had this and she forgot to take it back when she left me. Okay, so now her loss is my lab gain. Okay, so let's see what we can do here. All right. This could be awesome or it could be terrible. Let's see.
Ooh.
Kind of cool, right? I'm trying not to blow it out. I think that quality came out a little better, don't you guys? Does that look a little better to you?
Yeah.
Yeah.
I guess so, right? You can
There
see,
was a spectrum line at like 700, but it never showed up when you took the picture.
yeah, so a lot of this is a contrast issue. It must have been a red line you're saying, right?
Yeah, I don't know if anybody else saw that.
Let me try that again. I want to see that. I'm still learning how to do this through my phone. You know, it's like not easy to do this, guys. Let's look at that again. Hold on, I just got to get the right angle here. Yeah, I saw it for a second too, Joel. Let me look at it with my eye. It's definitely there, Joel.
Okay.
It's definitely, see, I can see it with my eye. The question is how to get it lined up with the camera and the exposure right. Let me go really bright. Got it. Hell yeah.
Sweet.
All right, there we go. Wow, those are bright as hell. All right, so we got a faint red line at 700. And then what's that other one at? What do you guys think? What's that other one at?
$780.
660.
No.
Hold on, you're reading it in
660.
the wrong direction, right? Yes, 600 and what?
60.
660, because seven goes in that direction. That's 650. So we got one at 700 and one at 650. Let's get those in first. This is fun. All right, so, or fun-ish anyways. So we got one right at 700. 620, 640, 660. We'll put one there, okay? Although this one was brighter. If we were doing it real badass, we would try to show the line strengths. Do you notice that some lines are brighter than the others? There's meaning to that. The ones that are brighter are more probable and they have more luminosity or intensity. I'm not trying to go too bazungu here, but okay. How about that? What would you guys say the color of that line is there?
I think that's
a gold.
It is kind of gold. It's funny when people look at it in the lab, sometimes like some people say it's orange and some people say it's yellow. So I like to see what you guys interpret it as. Of course, you're looking at it through the CCD. It's very golden so that it's just halfway between orange and yellow. So I'm going to actually make it golden myself by mixing orange and yellow. What would you say the wavelength is?
Like 580, 585.
585 is exactly, yes, 585. Okay, so let's try to start with yellow. This is helium, so there's 580. I'll just make it a little past 580. You can barely see my yellow, but what I'm going to do then to make it kind of golden, like Andrew said, I'm going to go over with a bit of orange to see if I can reproduce that golden rod color, something like that. Okay, that line is very bright. Let's see here. Okay, we got a couple of sort of tealish greens, one at 500 and one at, it looks like 490. Maybe I could, do I have a teal here? 500 is really teal. I have, maybe this is, what color this is cyan. I know how I'll make a teal. I'll do one at 500. I'm going to make one that's green at 500 and one that's blue at 490. but I'll make that 491 just a little bit greenish, so it's got a kind of teal edge to it. Sometimes I like to blend. Whatever. It doesn't have to be absolutely. This isn't, what do they call that thing? The Mary Kay thing where they tell you that you have a blue aura. We don't have to be quite that intense about our color selections. We have an indigo in a violet line. Let me look with my own eyes to see what I would say those colors are. When you look with your own eyes, one is a blue line at 470, and then an indigo line at 450. Okay. So when I looked through with my eyes, I'm actually going to just use indigo for both of them. So one was at 450, and one was at like 470. A couple of indigo lines. And I don't really see any violets. Okay, not bad. That was our helium spectrum. You guys got that? Okay.
And do any of those lines, are they significant like hydrogen?
Yes, if we knew more about spectroscopy, each of those lines are related to a different transition, say the 5 to 2 or the 4 to 2 or 3 to 4. But I know them well for hydrogen, but I don't know them that well for helium. We could look them up though. I just have to admit, and they will have different names. Like all the visible ones here are called the Balmer series. They have ones that for the ultraviolet spectrum called like the Lyman series. It gets pretty intense, Joel. This is your very first step into it. So, oh, geez, remind me to turn that thing off because that gets super hot and then I'm gonna burn my super fingers. So let me go get a hot pad. Otherwise I can't put in the next element. So 1 second here. I've got to remember to not leave that thing on because they get super, super hot. Let's cool down somewhere. Here's mercury. Ah, woo! Nice catch, B. See the color that mercury goes with? Kind of a bluish purple. Try this out again. This mercury is really shit in the bed here. Wow. I can see some yellows and some reds in there. but they're not really coming up on the camera. Let me get really close.
Yeah. I couldn't tell if they were like phantom
No,
lines or if they were actually legit.
I'm trying to hold this at the. Sorry, guys.
Looks like there's a lot of emission lines.
Some of it's contamination.
Okay.
What happens to these bulbs is over time they get contaminated with air, and then you start seeing the spectrum of air. And I've got to tell you, the spectrum of air is crazy. It has like 10,000 lines in it. So I have other mercury bulbs, but let's just see. I know, guys, this is a little tough. This is a way cooler lab to do in person. I don't know which view I like here. Wait, I want original. All right, so let's delete that. That sucks. That sucks. That sucks. Maybe that's one of the better ones. I am really, really displeased with this whole thing here. That was helium. That's one of our better ones. Let me see. Let me just check and see if I have another mercury in here, guys. Helium. Helium. I got like 10,000 heliums. Well, let's just do this for mercury, okay? Because I realize I'm taking a lot of time here. So I see a green line. What would you guys say that really bright green line is at?
.545.
That's exactly correct. So under mercury at 545, very bright. Delete that. We got another green at 500 and is that yet? Pardon?
575.
575.
Yeah, I think I heard you lower. 565. Oh, heck no. That turns out, it looks green here, but it turns out to be a yellow line at 575. You're just gonna have to trust me on that. When I looked with my own eye, that line was yellow. 575. I'm gonna just make it kind of orange yellow because the yellow doesn't show up that well. There's a couple of blue and indigo lines at 450 and at 470. So grab indigo, do one at 450 and one at 470. I think that might be just about all we can get. Let me be your eyeballs really quick. Oh, there's one at 400. There's a violet line at 400. Right on the nose. And that's our spectrum of mercury. All right, let's try neon. Hopefully this tube is cooled down. Let's grab a neon. It's going to be hot. Okay, you're not going to like neon, let me tell you. Although it's cool looking. Glows a cool electric red. Let me plop this thing over because I think that kind of helped a bit, that wide angle lens. And let's hold up the spectroscope.
Whoa.
Crazy, right? I'm trying to focus it. It's not easy to hold this, focus it, and take the photo at the same time. So you're going to have to really forgive me here. All right, let's see what we can do with those guys. Did any of these come out not like total crap? All right, that's stupid.
That's the best one.
That's the best one. Let me just do, that one's okay. I just want to, you can see there's a couple of red lines up near 700. In fact, let's start up there. I know there's like 2 red lines up here near 700, one at 700 and one at like 690. So let's get those first. So grab a red.
This is for neon?
Yeah, this is for neon. So there's one at 700 and there's one at like 690. Okay, now it looks like there's like 1, 2, 3, maybe 4 lines from 6.
Looks like there's one at 650.
Yeah, there's one at 650, and then there's like 4 more going out to about 6. Just trying to see which is the best one. 650, 660, 670, 680. We'll put about 4 in there. 650, 660, 670, 680. There's about 4 in there, so, okay. You can just see there's a ton in there. There's this. By the way, that person who just called me, that Jason Hathaway was one of my former students, and he recently just got into graduate school at some prestigious astrophysics university. So he's working on big name telescopes now. I'm going to be very jealous of what he's doing. And he was in my class maybe like 4 or 5 years ago, guys. It's crazy to think of how far Jason's come in such a short time. So keep doing what you're doing. We're going to just put a whole bunch. You know what we're going to do? We're going to put some red lines in, some orange lines, and some yellow lines. It's now getting to the point where we're just going to say, let's wing it. So put in a bunch of red lines. Okay. Let's grab some orange. And let's put in some orange lines. Okay. And let's put in some yellow lines too. And that's the spectrum of neon. Okay. Obviously, I would have held you to a slightly higher standard if we were using our eyeballs, but the camera makes it very difficult to do this. I want to show you one more thing, which is the solar spectrum, okay? Let me just give you a moment to catch up with Neon. You guys ready? Solar spectrum now? Okay. What we're going to do is we're going to kind of look outside at the sun. And believe it or not, all you need to see the solar spectrum is a view of the sky, which I have here. The white sky will actually preserve the reflected spectrum of the sun. I'm going to try to turn my laptop so that you guys can see me, but this is going to take a second here. I'm mostly worried about you guys hearing me speak. So this is Mercury. Sorry, I don't want these clanking around. It's Neon. Sorry, I need to pack these up so I can turn the laptop here. Bastard. All right. I want to turn my laptop so you guys can hear me talking. And what I'm going to, oops. Can you guys hear me okay?
Yeah.
All right. If I don't turn this towards me, we're not going to hear me very well. Let's try to look up. Get the fuck out of here. It's time for us to look up at the white sky, which preserves the spectrum of the sun. And I'm going to try to use this here. Zoom in. What kind of spectrum do you see there? Hold on. Now, there's a subtlety to the solar spectrum that does not quite get captured in my crappy iPhone 5 camera. My camera is kind of low resolution because I have an old phone, because I'm an old person. But at first blush, the solar spectrum kind of looks like the incandescent spectrum. But there are some subtleties which are kind of hard to see. Buried here inside of the wavelengths are these dark things called absorption lines. I was hoping that I might be able to pick a few of them up on one of my photographs, but.
Is there a couple in like 570 to 590?
Yeah, there you can see them with your eyes, like you can see them here and here. What they're supposed to look like when you look at them with your naked eye is, well, if you look at them with a very high resolution spectrograph, you can actually see hundreds upon hundreds of lines. And the sun absorption lines, some of them are quite dark. It's called the solar absorption spectrum. It's the Fraunhofer absorption lines. That's probably hydrogen alpha right there. And these are caused by atoms inside the sun, which are absorbing different wavelengths. So what we're going to do for this last spectrum is we're going to reproduce the VIBGYOR. I'll do orange. We'll just do a cartoon version here from 580 to 600. Do a little band of yellow from 560 to 580. We'll do a whole lot of green from 500 to 560. Just kind of make a quick incandescent spectrum. We'll do a blue from like 570 to 470 to 500, excuse me. Then we'll put some indigo in here and then some violet. Oh, can you guys see what I'm doing here? Okay.
Yeah.
I hope the recording captured that and not my screen.
Yeah, I think it did.
I hope so, because on my screen it wasn't showing it, so they missed that. I basically just reproduced the incandescent spectrum, okay? But now what I'm going to do is I'm going to take a black #2 pencil, and I'm going to make some absorption lines. Since we couldn't see them that clearly, we'll just kind of put them in random locations to show the concept, all right? Just put some absorption lines in there. And they're found all throughout the spectrum, actually. That's what makes it different than the incandescent. Incandescent spectrum is continuous. This is an absorption spectrum. So those are some of the more popular elements that we find in nature and inside the sun. And there's your lab.
Professor, I don't know if you remember this last year, but when we were doing this in our stellar system, I had a little problem looking and finding the yellow in the solar spectrum.
Yeah, I remember we were wondering if it was a bit of color blindness or what that was, right, Frank?
Yeah, when I was looking through that again, I still couldn't see the yellow. All I saw was a little bit of orange.
Well, the CCD sucked, but let me ask you this, Frank. Does this color look orange to you as well, or does it look yellow?
That looks yellow.
Okay. I think it was partially an artifact. You almost can't see the yellow. The CCD camera isn't picking up yellow very well. So I will tell you, you can see it looks a little bit more yellow there, right?
Yeah, I can kind of see that.
Let me look with my own
But
eye.
like, it's mostly orange.
Yeah.
Well, that's because yellow's an narrow band. I'll tell you what, you would see it a little bit more yellowish. I think what's happening is my camera is sucky. So it's not as good as the human eye. When I just looked at it with my eyes to confirm, I could see a little band of yellow in there. But I guess you're just going to have to take my word for it.
Alrighty.
The camera wasn't. You guys know how cameras reproduce color, right? Cameras use a Bayer matrix where each pixel is made up of two green pixels, one red and one blue. So come on, get out of here, Jordan. Okay, so they're mixing red, green, and blue, but because it's not a real yellow, they're kind of mixing and blending them, so the yellow kind of gets messed up in CCD cameras. I think that's what's going on. In any case, do you guys have all this? Did you keep up with me? Cool. Well, that's our lab for the day, okay?
Is this lab 6?
This is lab number 6. And that's what you should submit it as. Okay? So I'm going to stop share there. Put my phone back in its case before I break it. So that went, about as well as it could go. It's a very important lab for you guys to do because astronomers use that technique to identify elements inside the sun. Spectroscopy is very, very important in astronomy. Does that cover us, or are there any further questions?
For hydrogen, do we need all those little the little marks, like the, I don't even know what to call them.
Hydrogen alpha.
The H.
No,
Yeah.
you mean the labels? I mean,
Yeah.
if you can do it, that's cool, but it's not absolutely necessary. I thought it would be kind of neat, you know?
Yeah. Well, I just don't know what the marks were. I can definitely put them on. I just.
Hold on, I'm having some trouble with my doodah here. I called them, oh, you mean like the Greek letters?
Yeah.
Oh, it's alpha, beta, gamma. It's okay. Just do the colored lines if that's too much for you. It's all.
All right. Thank you.
My Zoom is starting to really act up here. It's like free. It's not responding. Can you guys still hear me?
Yes.
Yeah.
Yeah.
I'm getting a little worried that it's going to crash and I'm going to lose my recording. So, hold on. Let's see if I could. Oh, shoot.
It says you're still recording.
Right, but do you know how sometimes? Oh, there we go. All right, I'm going to stop the recording before this screws up. Oh God, please don't crash or I'm going to have a holy cow fit. Come on, buddy. Stop the recording. For some reason, my Zoom is acting up where, you know, sometimes you click and the wheel just spins and spins and spins and you get the frozen program. It's kind of doing that, but I'm just going to let it play out. While I'm waiting for the recording to stop, do you guys have any other questions?
I had a quick question, not regarding the lab though.
Sure.
Where can we see our midterm exam grade? I just didn't see it on the grades in like Blackboard.
There's the full grade center on Blackboard, but there's also